Okay, welcome to class. Happy Wednesday. Okay, to start with, can I answer any questions about the single crystal growth homework? Now that that's been posted and you've had a chance to look at it, are there any questions I can answer about that? It's due 3 weeks from today. The PowerPoint needs to be turned in the night before so that we actually have a chance to look through those. And then you have to bring your crystal to class on the last day of class, December 4th, where we will weigh them in order to figure out the moles of atoms that have been added, right? So we're not going to do this based off of mass. It's not like the heaviest crystal wins. Otherwise, you just pick heavy elements. It'll be based off of the crystal that has the highest number of atoms in it, right? Hence, we're going to convert it into moles. So you need to send your slide ahead of time the night before, okay? No questions on it? Okay, I think I might have added points on the homework. I might repost that homework. The only thing I've changed is I think I've put the number of points for each thing that I expect you to do, and they add up to 10. So I think that's the only thing I've changed. Yeah, Chase?
Is there a list of MSc students up yet so we can fit the needs for having multiple majors in?
How about this? Let's have MSc students who aren't in a group yet post that to either the discussion board on Canvas or Piazza.
Are there any of them?
Can you raise your hand, MSc students? MSc students that aren't in a group already. So maybe once they've joined groups, like if there are not enough MSc students to go around, then that's okay. Actually, it's like a 1-to-4 ratio. So in order for it to work, you could only have one MSc probably per group. But whatever. So do the best you can to spread out, and then we're okay. Okay, our learning objectives for today. We should get pretty close to finishing chapter 11 on kinetics today. The first thing we're going to go over again is Avrami kinetics with an example. And then we're going to dive into TTT diagrams for steel. So last time we left off, we said that anytime something transforms from one phase to another, it typically has this sort of S-shaped curve, right? When you plot it on a log plot on the x-axis, a log axis here, and then you have just the fraction transformed on the y-axis, going from 0 to 1 if it's fraction, or 0 to 100 if it's percent. Then it sort of has this S-shaped curve, and the mathematical expression that sort of fits that is the Avrami equation, which says the amount transformed at any given time, y, is equal to 1 minus the exponential of negative k times t time raised to the n, where k and n they're constants in that we need to fit them, but they're not constant over all temperatures. Ideally, they'd be time independent, otherwise this isn't going to work. But they are not temperature independent, okay? So because of that, we said in this example, where they don't show you the data for, say, 120 degrees, if you want to model your thing at 120 degrees, what you would need to do is determine k and n from this plot by reading points off of it, right, and solving two equations at the same time to solve for k and n. You need to do that for at least 2 different temperatures on either side of the temperature of interest, and then you could assume a linear interpolation between them, right? Even better, solve it for all the temperatures, and maybe you get it like a nice line, and then use the best fit of that line to figure out what k and n are at any arbitrary temperature. Are there questions about that? Because there will be a homework on it. Yeah? So k or n is what this could represent. You would not plot them at the same time. Do them separately. Yeah? It would depend. It would depend. Some, it might not actually. So what I suggest you do is fit it with whatever function gives a smooth fit between your data points. If that's linear, then use linear. If it's polynomial, use polynomial. Yeah? Nope, let me clarify that because we had a question. So this could be k or n, right? You could do those separately. Right? You could prepare one of those plots for k, prepare another one of those plots for n. They do not have to be the same value. They should not be the same value. N is typically a number around 1, And K, it depends on your transformation, but it's often a very small number, like e to the negative 4 or something. Yeah, Abby?
Could you give us two different plots then and have one compared to K and one compared to N?
I would give you data like this, the S curves here. I would give you these, and I would say, all right, now tell me the time for it to be 75% complete if it's at 125 degrees. And you look and you say, well, dang, I don't have 125 degrees. I've got below it and above it. So to answer this question, you know that you could maybe try and sketch this. That's not very accurate. So a better way to do it would be to start with 119 degrees Celsius, read 2 points off of this plot. You could say, okay, 50% is that value, 20 seconds. And this thing is maybe, call that 5%, is at 10 seconds. From those 2 data points, you can now write 2 equations with 2 unknowns. You can solve for K and N at 119 degrees Celsius. You do the exact same thing at these other temperatures, at least one other temperature on the other side of it. Once you have those, you have this plot. You can plot for K, what it looks like as a function of temperature, right? You can do the same thing for N, and it's going to have a different dependence. And you're going to take some value in between those. I suggest doing more than 2 temperatures, right? Because it's going to be better. Like, you don't know if this is a linear or if that's a polynomial yet. But if you do all the temperatures, then you can fit it. Can I answer other questions about this? Avrami equation? So this is not a first principle. We're not saying, like, first principle means that based off of the fundamental aspects of chemistry happening here, or physics, that we know how it happens. This is just a mathematical model that happens to fit our data, which we love as engineers. If you're a scientist, you want to know the fundamentals. If you're engineers, you just say, give me something that fits, right, that works. That's what this is. This is something that turns out to be a pretty good estimate of how things transform, okay? So let's do an example, okay? The clicker question we're going to start with says, if a polymer has the kinetic Avrami equation N value equal to 1.7, so that N is 1.7, and it says it takes 100 seconds for the polymer to 50% crystallize, how long would it take to crystallize 99%? So first thing you're going to do is write the Avrami equation. Try that one more time. I'm going to get that started while I figure out what's wrong with my pen. Are you not connected?
I'm connected, it just keeps saying that.
That's a bad day for it because we're going to do like a gazillion today. So you have to send me an email and I'll just give you points for them. So after class, make sure you send me an email. Okay, another minute or two. Okay, get your answers in. Okay, we're going to close the poll. Okay, yeah, 90% of people are calling it an answer pretty close to the actual one. I get 304 seconds, 305 seconds, and most people are getting about that. Okay, any questions about the Avrami equation? About these types of problems? So again, the big difference between this one and the one that'll be on the homework and potentially on a test will be I might have you solve for k and n using some sort of interpolation between other data points. Okay? All right. Keep going. So I get 304 seconds or so. Okay? Okay, we've mentioned last time that if you quench something quickly enough and it never touches that, what we call the nose of the TTT diagram, then you never get transformation, right? The TTT diagram were these things, right? Where because there is a maximum rate at some temperature in that top plot, in this lower plot, that means that there is a minimum time until transformation. If you cool it down fast enough that you never touch that, because this is time on this axis, then you never get transformation, and you'll get metastable structures, okay? So this is one of the reasons why we keep on showing you phase diagrams, but in fact, they represent under equilibrium conditions, and lots of times things don't reach equilibrium. They take too long and they don't ever actually get there. A good example is in this steel phase diagram, okay? So in the steel phase diagram, we have a eutectoid reaction where your gamma turns into ferrite plus cementite, and the compositions are listed there, right? So for that reaction to take place, think what has to happen. There's a diffusion involved, right? Because your gamma is 0.76 weight percent carbon, but your ferrite has almost no carbon in it, 0.022, and your cementite is 6.7. So in order for that reaction to take place, you literally have to diffuse carbon atoms, right? They have to separate, and that's going to take time. Because it takes time, it's possible to do this quickly enough that diffusion can't happen, and instead of getting the types of steels that we're familiar with, you can get a totally different type of metastable steel, which we call martensite or martensitic steel. Anybody use this? Anybody work in industry where this is a thing? It's the hardest steel that you can make, and we'll explain why in a moment, but it's also the most brittle, okay? So here's a diagram of what it might look like if you were cooling things down. The transformation for this eutectoid transformation in steel happens at 727 degrees. If we pulled up the phase diagram, that's where that flat line is where the eutectoid reaction occurs. So the second that you start going below that line, this dashed line right here, the eutectoid, from a thermodynamic standpoint, it means technically you should start, you could eventually transform. But from a kinetic standpoint, that could take a really long time, right? These lines shown in red here, right? This one right there, that represents probably 1% transformation, or in other words, when the transformation is sort of kicking off. If you're only a degree below this, you might have to wait a very, very long time before that thing ever transforms, which is why you can supercool things. You can cool them a little bit below their thermodynamic temperature, and it could just take eons before it actually transforms, right? On the other hand, if you cool it down to this temperature, if you could take it out of the furnace and then put it exactly at that temperature, it takes about 1 second before it transforms, right? And this is because different rates are available, and the different rates exist because there's different temperature dependence of nucleation and growth, right? Any questions on that review from last classes, Eric? Or Andrew?
What happens below where the line's cut off?
So what happens below, we're going to fill that out in a minute. Yeah, that's the nose of the TTT diagram. We know it's going to bend back, but it does some other stuff too. So let's take the example as they go from point A to point B. You've cooled it down. Before it touches that line, if we zoom in on this, right, before that point C, when it touches that line, if you're holding it at that temperature, it's still pure gamma phase because it's never touched another line, so it's still that austenite. It hasn't transformed yet. The second it touches that line, it's going to start to transform. We know it's going to start on the grain boundaries because those are the things that cost us the most energy. That's why you can see, like, if I draw them in green, this is where the grain boundaries used to be in that diagram, right? It's going to start to grow on those, and it's going to be the lamellar structure where it forms, okay? Then what we see is that as it continues across from point C to point D, it's going to continuously transform. The dashed line represents 50% transformation, and by the time it touches point D, it is now completely transformed to a mixture of ferrite and cementite. Now, because this is happening above this nose of the TTT diagram, it's happening above that point, the structure that forms is what we call pearlite. Pearlite. So if you've heard of pearlitic steel, pearlite steel, they call it pearlite because it looks a little bit like mother of pearl. If you've ever seen mother of pearl, it kind of has like, you can see like layering. They can see the layering. In this case, you can see the layering from the lamellar structure. It's happening at high temperatures. That means that there's lots of diffusion possible. So the thickness of those layers is very thick. Okay? If you do this below this nose of the TTT diagram down here, the same thing can happen, except the thickness of those lamella is much more narrow because there's less temperature, so it can't diffuse as far. So you get really fine-grained lamellar structures. Okay? Any questions on that? On bainite versus pearlite? So the lower, if it happens below that point, we call it bainite. If it's above that, it's called pearlite. Okay? And we'll show you on another diagram where it's labeled. Any questions on bainite versus pearlite? It's the exact same phases. It can be the exact same weight fraction of the phases. It's just that one is really fine, like fine zebra stripes versus big fat zebra stripes. Okay? All right, let's keep going. So TTT plots are valid for a single composition only. If you're talking about a different type of steel, right? If we go to our steel phase diagrams here for a minute. The TTT diagram that I just showed you, it would correspond to a very specific composition of steel. For example, that I think was like right at the eutectic point. In fact, yeah, I know it was. It was right at the eutectic composition. But if you're to the left or to the right of that point, you need a different TTT diagram. How do we know that to be the case? Well, think about it. If you're over here and you start to cool down, way before you get to 727 degrees, you cross another phase boundary, right? When you're here, if you can see that little finger's pointing over there, you should have a mixture of gamma plus just pure cementite, right? And that's not shown on this plot. Like if you look at this plot, you go from gamma, austenite, to a mixture of cementite and ferrite. There's no region here that represents just cementite. So because of that, we have to have a different diagram for different compositions. Here's an example of one, right? This is a non-eutectic composition. How do we know that? We'll take a look at it. When we look at it, the eutectoid temperature is labeled, right? This is the same thing as before. But look, if you're above that temperature and you hold it for long enough, you start to get something. What do you start to form? Well, they've got it labeled on the top. They've got it labeled A up here. And then the first region that you break into is A plus F. What do you think F stands for in steel? Ferrite. Cementite's going to be C. Ferrite. So what type of composition would this be? If you had to guess, let's go back to our diagram. If you're cooling down and you're above, again, this is the eutectoid temperature, that big flat line. If we form ferrite before anything else, are we to the left or the right of the eutectoid composition? We must be to the left of it. This is what we would call a hypo-eutectoid steel, TTT diagram, right? And again, you can see that even when you're below this, the first thing you're going to form is some of that ferrite, but then it transitions, there's these other lines. This would be the start of forming pearlite. P stands for pearlite, meaning it's ferrite, but it's also cementite in that lamellar region. And you can see here in the final product, if you let this thing sit for a long time here, and you get to that point, the final product is not just pearlite. Up here, on the one above it, it was just pearlite out here. You get what we call coarse pearlite, the big fat grains. But there's no A there for ferrite. Here, you do have F plus P. What is the F talking about? What F is that? There's another word for it that we called from the other chapter. It's our pro-eutectoid ferrite. Remind me what pro-eutectoid meant? It's the stuff that formed before the eutectoid, right? So if we come down to the left or to the right of this, you will have something on the grain boundaries that isn't the zebra striping. That's your pro-eutectoid, either ferrite if it's to the left, cementite if it's to the right. And then, if you keep on cooling it down, all of your gamma, your austenite, will transform to a sort of zebra structure, and that's the P, the pearlite there, okay? In this case, they have it down here lower, the same sort of thing. They have A plus B, and that turns into B. That should technically be A plus B out over here. But B is for bainite. Okay, we're going to show you some more diagrams of these in a minute. This is a more typical steel TTT diagram. This is right at the eutectoid composition. And again, you have, in this region, you've got gamma turning into pearlite, as it's labeled here. But if you're below the nose, it's gamma turning into bainite. Pearlite versus bainite. See if we can find a nice micrograph showing this. They look very similar. It's just the size. Yeah, right here. So you can see if pearlite has kind of big stripes, bainite's the same thing. It's just much, much smaller, right? And then there's something else called martensite we'll describe in just a second. But real quick, would you predict greater strength for pearlite or bainite? Bainite, why? Yeah, you've got more imperfections in this structure, more grain boundaries. That dislocation is going to have to traverse those. And if it's harder for that to do it, then you made it a harder material. Which one should be more ductile? Just the opposite. Pearlite should be more ductile. So this is interesting. All of a sudden, you can quench steels at different rates, right? You could quench it really quickly and then hold it, and you get bainite, a strong but not super ductile steel. If you later on say, shoot, that's too brittle, it's breaking, you don't have to buy a bunch of new steel from wherever you're buying it from. You could take that steel, you could heat it back up, and it's going to coarsen, right? The bainite will coarsen into pearlite. Those things want to get rid of surfaces. The surfaces cost them energy. So if you heat it up and let it diffuse, they're going to coarsen, and you can go from a brittle hard steel to a ductile but weaker steel just with a heat treatment, okay? Sometimes you don't mean for this to happen, but it's just you can't avoid it, like when you're welding. When you weld something, you're locally melting it, so there's going to be what's called a heat-affected or a heat-treated zone. In that heat-affected zone, do you expect it to be harder or stronger? Stronger or weaker? Weaker in terms of what I just described, because it should coarsen. What actually might make it weaker for other reasons in the heat-affected zone? Yeah, what do you think, Landon?
Well, when you heat it up, it makes it easier for like dislocations to travel through, so it kind of like makes it a little bit softer, and then it hardens again, it cools with that easier dislocation.
Yeah, so we've undergone recrystallization or recovery. Yeah, you've recovered that region. So not only have you coarsened it, but the heating can also cause recovery. which is just reducing the density of dislocations. So 2 reasons why it might be weaker. What else might be a reason why it's weaker? Anybody welded much before? I don't. But Carlos, what do you got?
When you weld, sometimes you can get little imperfections of air.
Yep. Yeah. Imperfections are really common around welds. So if you have a pore, right, you're melting things. If there's a bubble that gets caught in there, or impurities, if you form some oxide, all these things can be weak, statistically the flaw that causes your thing to fail. Okay? There's another phase we haven't talked about called spheroidite. Spheroidite is kind of what it sounds like, spheroid. The mixture of ferrite and cementite, if you hold it long enough at high enough temperatures, they're going to try and reduce their surface area. And the way that they can maximize the reduction in their surface area is by forming spheres. So it goes from being this nice like zebra structure, it just actually forms big globs of ferrite and big globs of cementite next to it, right? This is the worst type of steel. If you take steel and you hold it for a really long time on this plot, spheroidite would be like out here. Spheroidite would be in that region, meaning really high temperatures, really long time. Technically, it is a mixture of ferrite and cementite, but you held it at such a high temperature that those phases totally segregated in order to reduce surface area, and you get really a crappy steel. It's just really weak because the strengthening comes from these sort of lamellar layers. When you get rid of those, you might as well have iron at that point. Iron with chunks of ceramic, and it's even worse, right? So it's not doing it for you. Okay? Martensite. So this is the more complete phase diagram. You notice there's something else going at the bottom down here. So we quenched it. We quenched it quickly. We missed the nose of that TTT diagram, but on its route to becoming down to room temperature, we now cross different lines. The lines you see there correspond to gamma turning into martensitic steel. So this is where it's going to start at maybe 210 or 15 degrees. And as you keep on cooling it, that transformation is going to be complete around 100 degrees. And here's room temperature down here, right? So you no longer have austenitic steel. You have martensite steel. What's good or bad about that? Well, martensitic steel is interesting. It's what we call a diffusionless transformation. In fact, that's a general term. Martensite or a martensitic transformation is a phase transformation where there's no diffusion. The atoms just all shift a little bit. The way that it shifts for us is it goes from FCC, face-centered cubic, to body-centered tetragonal. So here they show FCC alone. You can see where the atoms are located on the faces. Here they're showing 2 FCCs next to one another, and then they're showing, they've drawn an additional little rectangle in the middle, and you can see that actually is tetragonal. This side right here is shorter than that side. It's shorter than that side. This is either tetragonal or it actually would be tetragonal. Let me redraw that. It's just the perspective that they chose. These are actually the same length, those 2 sides, but that's different than this length. So in order for this to happen, your cubic unit cell just has to shift up a little bit, right? In the vertical direction, if it shifts a little bit up, then you go from an FCC, a cubic symmetry, to a body-centered tetragonal, where now it's tetragonal with 1 atom in the center. You see that? This volume expansion, as it gets a little bit longer, that volume expansion causes cracking in your material. So austenitic steel, when you convert it to martensite by quenching it really quickly, it's actually filled with cracks. It's actually the worst. It's not a good steel. Because all those cracks are obviously going to weaken it. Now, on the plus side, we remember from a couple chapters ago that the ductility is proportional to the slip systems available to it. And cubics essentially have like the best slip systems. There's tons of them. So these tend to be relatively ductile. But tetragonal does not have nearly as many slip systems, right? Because you've changed the symmetry. So if we did our calculation of the highest planar density, highest number of directions, this just has fewer than that. So it's already going to be more brittle. But then this has the carbons that were occupying the interstitials. So here they're not showing you the carbons. Here they're showing you where the carbons would have sat in regular steel. So here's just pure iron. Now we've made steel by putting the carbons on here. Those carbons make it even more brittle. So this thing is just like as hard and brittle as you can get. And it's actually not very useful if you don't do something else to it. So what they do is they quench it down. You get pure martensite. And then they actually heat it back up. And they do a heat treatment to cross it into bainite. We don't call it bainite. We call it tempered martensite. You made martensite, and then you heat it up at a really low temperature, like a couple hundred degrees is all. And then you technically you're converting it into ferrite and cementite. So we would normally call that bainite. The difference, though, is that instead of being lamellar, it's precipitates. So again, if this was our structure, we had this guy. Now we're going to heat it up at such a low temperature that the carbons can't form big sheets like the zebra stripes. Instead, they form little tiny precipitates. So those little tiny precipitates do a hell of a job to strengthen your material. So tempered martensite, you heal the cracks a little bit with this process, and you end up with sort of the best case scenario if you want to maximize both ductility and strength. You can't do better than tempered martensite. Okay? Can I answer any questions? Tyler?
We're talking about the difference in strength of these different phases. How different are we talking? Like 100 megapascal?
I think I've got some plots that show that. It's significant. If I don't have them today, I can find them and let you know. But it's pretty significant. Like, there can be big, big differences. Abby? Uh-huh. Yeah. So let's zoom in and take a look at these. So here's pure iron. This would be ferrite. That is ferrite. Oh, sorry, not ferrite. Ferrite is the body-centered one. At high temperatures, it goes from body-centered to face-centered cubic. This is austenite. Okay. But steel is not just pure iron. We add carbon to it. When you add carbon to it, let me change the color of the carbon atoms so it's easier to see. Here's our carbon atoms, right? They've only drawn a couple, but that's where the carbons would be. They're occupying the interstitial sites. If you take this cubic structure and you stretch it vertically just a little bit, then technically you end up with a different symmetry. It's now tetragonal. Those are where the carbons are at. And this, because we changed the symmetry and it has different slip systems, that's one reason why it's more brittle. It has carbon occupying the interstitials, which also makes it brittle. And the volume expansion put cracks in your material, which also makes it brittle. So there's 3 reasons why this thing is just not good in the pure martensite form. So instead of using it in that form, we heat it back up just a little bit, and the iron is going to separate into regular old ferrite, BCC iron, and the carbon's going to separate into little tiny dispersions, which are just nanoprecipitates of cementite. One second, I'll get to your question. Zubai, Alex. So tempered martensite microstructure. Let's see if we can find a good picture of this. I don't know if we will, because it's really small, so it might be hard to see the precipitates. You're looking at tiny little precipitates. See the difference there between like the zebra patterns we've been seeing? These things are like little tiny cementite regions in a matrix of ductile body-centered cubic ferrite. This is sort of the best case scenario. You get ductility and strength from this. The precipitates have they have a strain field around them, right? Because they don't match the lattice perfectly. So there is a strain field which is going to inhibit dislocation motion. That gives it its strength. But you've gotten rid of all the cracks and stuff from the body-centered tetragonal. Alex?
How does it expand while it's
Oh, great question. Yeah, so we did this in class, right? With the iron wire demo. I guess I melted it, so I showed you the video. But the wire, imagine it's in its hot state, so it's in austenite. Austenite is a more collapsed structure, right? It's more densely, FCC is more densely packed than BCC. It's like 0.74 versus 0.68 packing. So then when you cool it down, it goes from FCC to BCC, and in doing so, it has to expand. It's a more open structure. So even though you're cooling it down and you think, oh, things shrink upon cooling, there can be a transformation where they don't. So the plot might look something like this. If we were going to plot thermal expansion, let me go to normal view. Okay. Let's do this real quick. Thermal expansion, you might typically, if you're plotting like delta L over L as a function of temperature, we're going to start at high temperatures and we're going to cool down. So a normal material with no phase transformation would look like this, right? It doesn't have to be linear, but its delta L is going to shrink, right? It's going to go down as you go down in temperature. But if there's a phase transformation which causes an expansion, it's going to look like this, and then it expands, and then it goes down, right? And it's the opposite going up. When we take that exact same iron wire, we were heating it up, so it's getting longer, its expansion's going up, but then it got shorter all of a sudden. It shrunk, and then when you heat it up, it continues to expand again. So think of it like an event. It doesn't happen at a single temperature. It can happen over 10, 20, 50, 100 degrees, depending on your transformation. But it's an event that happens in otherwise expectable, predictable behavior. That's a great question. Can I answer anything else about this? Yeah, Emma?
What, is there a use for the steel with the precipitants in it?
Tempered martensite. Yeah, it's a fantastic steel. It's very strong. It's still not super ductile. If you need a really ductile material, you don't look at tempered martensite. You would look at pearlite, right? Or somewhere between pearlite and bainite. But if you want a really high strength, like tool steel, yeah, tempered martensite's pretty great. Okay? Let's do some examples, okay? Let's talk about how we would get different regions. Let's see. Yeah. So we're going to do this with some clicker questions. So the first question here says, predict the microstructure for A. Okay? I don't know if you can see that super well. Can I see that? Okay. Predict the microstructure for A. That's the dark blue line. You basically cool it below the eutectoid temperature. You hold it for a very long time, and then you quench it. It looks like it doesn't get to that bottom line to me, right? And then you quench it, right? What structure do you end up with it? Is it spheroidite? Is it 100% coarse pearlite? Is it 50% coarse pearlite, 50% martensite? Is it 50% coarse pearlite and 50% bainite? A, B, C, or D for that? Again, we're talking about the dark blue line. You hold it. It doesn't, to me, look like it touches that red line on the bottom side here. It doesn't quite get there. And then you quench it straight down to room temperature. Okay, get your answers in. Okay, we're going to close the poll. Get your answer in. Okay, I'm going to close it. So this, to me, should be C. Yeah, most people think C. Let's do another one. All right, how about this one? You're going to predict it for B. B was right next to A. Basically, you quench it, just like before, but now we're going to heat this thing back up and we're just going to let it sit for like infinite time. Is it spheroidite, coarse pearlite, a mixture of coarse pearlite and martensite, or a mixture of pearlite and bainite? Again, B, we're letting it sit a very long time at a very high temperature. Get your answers in. Okay, I'm going to close the poll. Okay. People better think A, mostly A. Again, whenever I say that we hold it an extremely long time at a very high temperature, coarse pearlite, I'll go back and give you credit for that, but it's really going to be spheroidite. So I'll update the score on that one, but you should say spheroidite. How about this next one? Predict the microstructure for C. Okay? C in this diagram, you quench it to 600 degrees. We're in this imaginary world where you can quench things instantly. That doesn't actually exist, but for right now, we're assuming we can. You hold it until, 4 or 5 seconds. Then you quench it instantly down to a different temperature, and you hold it for that long, and then you quench it all the way down. What will be the microstructure? Will it be spheroidite, coarse pearlite, a mixture of coarse pearlite and martensite, or a mixture of pearlite, bainite, and martensite? How do you go back in time? That's how these diagrams work. So on these diagrams, every time you change the temperature, you just reset the clock. That's the rule with these TTT diagrams. You reset the clock and go back to 0. Well, it doesn't go to 0 because it's a log plot, so it can't, but you know what I mean. Okay, closing the poll. Okay, why is that the case? That's right. So you convert 50% of your austenite into pearlite because you touch that dotted line in the middle, which is the 50% point. So 50% of your austenite is still there. If you then cool it down to a different temperature below the nose of the diagram, you convert 50% of what you had left over. You'd already converted 50% of your austenite, so now you're converting 50% of 50%. That gives you 25% bainite. And then when you quench it, the final 25% of austenite is going to transform to martensite. Okay? Let's do another one. All right, this one's for D. If you look at D, it's the magenta line where you quench it somehow instantly. You hold it for a couple seconds, then you quench it instantly down to room temperature. Do you end up with A, B, C, or D? Okay, I'm going to close the poll. Hopefully people think this was martensite, and yeah. Okay. So we could go on. I'm just going to, there's a bunch more of these. I'm just going to post them as reviewable on Top Hat. So anytime you can go back and look at what the correct answer of them would be. But for the sake of time, we're going to keep going. Are there any questions on using these TTT diagrams? Are they pretty clear? Yeah, Abby? Okay, the last one we did, if you look at it, at no point did it, even though we quenched it and we held it for a while, it never touched that red line right there, which would be the start of turning into bainite. So it's still in the austenite phase since it hasn't technically touched that point yet. So if you cool it down, then the first red line that it touches is the M start for the start of the martensitic transformation. And then it goes down all the way through complete martensitic transformation. So it's pure martensite. Jaden?
This question might not be applicable because that one, the green line went back in time.
Okay.
So when it first hits that point, when it first hits the 50% line, going back, does it not like reverse? Would that not reverse the solidification?
No, because we're going down in temperature. Reversing the solidification would have been heating it up above the eutectoid temperature again. It's not solidification. It's going from a two-phase into a single phase. So it's still, they're all still solids, but I see what you're saying. If you were to heat this thing back up above the eutectoid and let it sit long enough, it will become pure austenite. And then if you quenched it down to the blue, the second green line right here at 450, then you'd end up with 50% bainite. But because we didn't do that, we basically took it from one furnace at 600 degrees. We put it in a different furnace at 450. The stuff that had already transformed from austenite to coarse pearlite, it's still there. We can't undo that unless you go back and you heat it up again.
But so this green line wouldn't actually happen in life because it goes back in time?
So the time thing's tricky. Think about it like this. Like you literally took it from one furnace into another. At the moment you put it in there, that's time t equals 0 in that furnace. The austenite that is exposed to that temperature is starting from 0 time and moving forward. Okay? Yeah.
What would happen if you left D like 200 degrees instead of quenching it more?
Okay, so if you left it there, I don't know. At these interfaces, I'm not enough of a metallurgist to tell you that answer. I could sort of snoop into it and try and find out, but I'm guessing you'd end up with something, you wouldn't get the full tempered martensite, right? But you would probably get precipitates and some degree of bainite, is my guess. I'm totally guessing, though. Okay? Other questions about this that I can answer? So in the real world, we don't have this magical ability to go from instantly one temperature to another. Even if you take it out of a hot furnace and put it into a different one where the temperatures are different, your material is still at the previous temperature. And it's going to take a while for it to change temperature. In fact, we did a whole chapter on that. Fick's second law, right, for temperature tells us how quickly the temperature profile will change in your material. And it's not instant. Even diamond is not instant. So these are interesting conceptually, but they would be more useful if they reflected the reality that you can't change temperature instantly. Instead, what we have is continuous cooling, right? So these diagrams are called CCT, continuous cooling transformations. These are much more realistic. These show you the exact same idea. You have temperature on the y-axis. You've got log time on the x-axis. You have regions representing the start of different transformations. But what you have here is a series of sort of S-shaped curves, right? They're sigmoidal curves that represent different continuous cooling rates, right? So if you sprayed different coolant on your metal, right? If you took it out of your oven, you could use a really low cooling rate, like 0.0125 centigrade per Celsius or per second. That's not a very aggressive cooling. Or you could blast it with cold water and get a very aggressive 46 Celsius per second, right? So if you follow along these lines, you find the one that's closest to your quenching rate. These are more accurate TTT diagrams. And it just shifts things over a little bit. It's the exact same idea, though, as before. What they haven't shown you here is like the middle dashed line and the final line, but other ones might. This is just not a great one. Yeah, Chase?
And when you're looking at the temperature of whatever you're like doing this with, whatever sample, is that theoretically the average temperature? Because the outside is going to be different from the center, right?
Yeah, so it's kind of a loaded question. You don't have to have your material be all the same thing. So in other words, if you took a piece of metal, you're making a sword, right? You could quench it, right, into a really aggressive environment, something that's going to pull the heat out fast. So at the surface, maybe you're getting martensite, which probably you want if you want a sword, because you want to put a hard edge on it, and you need a hard material to put a good edge on it. But the bulk, since the heat has to diffuse away from the bulk into the quenching medium, it's not being quenched as quickly. The inner part of your blade might be somewhere over here, which is probably exactly what you want. You don't want your whole blade to be hard and brittle like a ceramic, or that's just a bad sword. It's going to fracture. What you want is your surface to be hard and your bulk to be some of that bainite or pearlite, which is going to give it toughness. So I see what you're asking. Like, there's a temperature profile in your sample. You're exactly right, and because of that, there will be a composition, a microstructure profile in your sample. The surface might be one thing, the bulk might be another. So on the question that we asked you on the homework last time, it kind of got into that, right? When you flash freeze people, which they're trying to do, the problem is if you flash freeze them, the skin gets a different treatment than the bulk of your body because heat diffuses through your skin differently. So the outer layer has a different, basically, experience than the inner bulk part. So they can flash freeze really small things, but not really big things because of this problem. We're out of time, so we'll do a little bit more on Chapter 11 next time, not much, and then we're going to move to Chapter 12.